All right, since everyone that counts is here, it's important. All right, so let's see. Class?
Yes.
Thank you. All right, so 2.2, the derivative as a function. Now, this is what I've been talking about, doing that voodoo magic, where we get some like seriously weird math, or we take an exponent, multiply by what's out front, then subtract 1. Yeah, that's this. So the whole thing is actually find the derivative is we're taking the number as h approaches c, where it is going to get closer and closer together, where we get this right here, which is the same as saying f prime of c. Means something. Find the derivative of the function at any real number c. So what I'm going to do is I'm going to do the voodoo magic here. So I'm taking this, so I'm going to say f prime of x is equal to, okay, let's do that first part right here. My exponent is 2, so where does that go? So it's 2 times, which is 2, and what do I do with my x? Subtract 1, right? Yeah, so x to the first. Okay, and right here, this is going to be minus 5x. And so what do I do to that? What I what? So what's my exponent right here? 1, right? Which is? And what do I do with my exponent? Subtract 1. So that's going to give me x to the x is 0, which just goes away, right? So, right there. So now if I'm doing it at c, any real number c, this is important. So, f prime of c of any number, 2 times c minus 5. So any real number, I would just plug it in there, and that would give me, remember, definition of this, right here. The derivative is going to give me the what? Slope, right? At any given point. It's going to give me the slope at any given point. That's important. All right, this one right here, this is another weird one. We started this the other day. So I'm going to rewrite this as f of x, and now that's going to be x to the what power? 1/2. So same rules apply. Even though that it is a fractional exponent, the same rules must apply. So what do I take to that 1/2? I move that 1/2 out front, right? So I get f of x, so f prime of x is equal to 1/2 x to the, I'm subtracting 1, right? So my subtracting of 1 is going to look like this. It's minus 2 over 2. Minus 2 over 2, which is going to give me negative 1/2. And to rewrite that negative 1/2, where does that need to go? As a positive exponent, that would go where? In the denominator, right? I would move that down to the denominator, and that would make it a positive at that point. So that would give me 1 over 2x to the positive 1/2 down here. Yes, no, maybe? Good. So, determine the domain. Okay, so what numbers am I allowed to have in the domain? So we're the domain of f prime, right? 0? Can I have 0? Can you have 0? Okay, Tree says yes. Can I have 0 in my domain? Tree says yes. Everyone else is just going to go with Tree? Christian, you agree? Huh? Okay. Vincent, you're shaking your head. No? Why?
0 center place at the bottom and then 0 at the denominator.
If I plug in 0 for my domain right here, can I have 0 in the denominator? No. 2 times 0 is going to be? So that would be undefined. So is 0 in my domain? No. Will it be close to 0? Can I use numbers that are not 0? What type of numbers can I use? Can I use negative numbers? He's saying yes. He's saying no. Can I use a negative number? Don't forget, what does this thing right here actually represent? A square root. If it represents a square root, all square roots rules apply. So can I have negatives in there? I cannot have negatives. So if I cannot have negatives, but can I have positive numbers? So my domain is going to start at 0. Is it bracket or parentheses? Parentheses, because it's not equal to 0. And my domain is positive numbers, so that would go to positive infinity. So, no?
I heard a really deep voice behind me.
Might be the voice in your head.
I got scared for a second. I was a 40 years old chain smoker.
Voices in your head. So, you have the demon speaking directly in your head right now. Are they speaking in Latin? Okay, yeah. Gets crazy if it does. Okay, all right. So, that would be the domain of this. Now, another way of actually writing this would be x such that x is all real, and that has to be greater than 0. Yes? Now, does that make sense? Have you guys seen it like this before? That symbol R, it's like a dollar sign, but it's an R with a line through it like that. So yeah, that's a symbol for real. Alrighty, let's keep going. Interpreting the derivative as a rate of change. The surface area, that's important, area is always units squared, right? Okay, that's important, especially when we're talking about different things. Area is a unit squared, so when I'm talking about that, it needs to, everything match. S unit squared of a balloon expanding as a function of time, seconds. So I get S of t, S of t, 5t squared. Find the rate of change of the surface of the area balloon with respect to time. What are the units of this? Now, again, you have to pay close attention to the units. Okay? So, sometimes you're going to be given problems that have area, but I'm going to give you a radius instead. Is radius an area? Say no. Radius is not an area. It's a distance. It's linear, right? Ooh, right in the back.
Steal his space.
Okay. Anyway. So, right here, we're going to go ahead and continue this. So, S prime of t is going to be equal to, what do I do with my exponent? Out front, right? So, it's going to be 5 times 2, which is 10 t. Now, this balloon is expanding, right? So the balloon's expanding, so the surface area is just the rubber of the balloon, right? So the area is expanding. Sometimes we will actually have some of these problems when we come up into some of the different stuff later on. You're gonna have to look at the area of the balloon as the volume of the balloon changes according to the radius of the balloon, which is linear. So that's 3 different types of units. We have a linear of the radius, we have the area squared of the surface, and we have the volume, which everything, the capacity of the balloon. So pay close attention. So right here, so rate of change, this is going to be 10t. My units are going to be meters. It's a rate of change, right? It's a rate of change. So whenever you hear rate of change, what did I say that you should think of?
Slow.
Miles per hour, right? A rate of change is miles per hour.
Okay.
So that tells me that miles per hour is distance over time. That's how I always trick myself into doing this. Rate of change, miles per hour. Distance over time. My distance, or in this case right here, it's going to be meters squared per second. Yes, no, maybe? Possibly. Hopefully it's not too bad. Graph of the function and its derivative. So this is actually really important because a lot of times you're going to be given one or the other without any functions. So I'm going to start with this one right here. What do I know about the slope of this thing right here? Right there, just in red. It's going where? Christian, where's it going? It's going what? Yeah. Okay, so whenever you're talking about slope, I want you to do this. So that's my, it's a me, Mario. It's a very bad Mario, but what? Wow, that was a horrible Mario. Hold on.
Did you say that? Much.
There you go. There you go. It's a me, Mario. I grew up in the age of a 2D side scroller. All the coolest games were two-dimensional side scroller running from the left side to the right side of the screen.
Big blue with Minesweeper and the farm animals.
Okay, whatever yeah, what that guy said. Anyway, so I tricked myself into always thinking 2D side scroller. I got Mario, and he's running from where? Going from left to right, isn't he? So going from left to right, Mario gets on right here. What's he doing? If he's walking along the line right here, he's going down, right? So the slope is going to be negative, right? So right here, this slope is negative 15 right here. Way up, oh, close enough, right? Right, like way over here. That's negative 15 there. So right here, the slope is the slope is, okay, you notice as it's going, right? So this slope is going down. Now, the one in blue, let's go ahead and look at the one in blue. I'm going to change up colors here. This ugly green, I really wish I had a better green. What is happening right here? What is happening right there? Think of my little Mario. He's going from left to right. And if he's walking across that spot right there, is he going up or down? He's not going up or down. That means that the slope is 0. It's a nice flat surface, right? That's important. So right there we have a nice flat surface as we're going. So let's go over the entirety of this. So this is now my original function. So here is a function, and we're only going to talk about this piece right here in purple. Okay? And think of Mario. I will sketch my Mario again because my Mario is pretty awesome. Gotta have that huge hat too. Anyway, there's my Mario. My Mario is going this way. So, Mario's taking the purple line, right? So as he's taking the purple line, the slope is, look at it, the slope, he's going to be climbing up, isn't he? So if he's following this line, he's climbing up. Okay, so we're up, up, up. So that tells me right here, my slope over here is, it's all positive, right? That's important. So we're not actually talking about increasing, decreasing, all that other stuff yet. Right now we're just talking about it is positive slope because he's climbing up right here till he gets to that point right there. And then he will continue at that point and he will keep going up again. He will continue going up right there. So he's going to go all the way up. So now from here, is there any place on this graph where he's going to be going downhill? He's not going to go downhill at all, right? All right, so I'm going to, right here, x -2 there you go. So this is f of x, f prime of x. F of x. So f of x at -2, this is my function f of x. This is my function f prime of x. So I'm going to plug in -2 for this. -2 to the third power is -8. -8 minus 1, -9. So this is my function in red that I'm doing here. Do it again. -1 to the -3rd is going to be a -1 minus 1 is -2. 0 to the -3rd is 0 minus 1, -1. 1 to the third power is 1 minus 1, 0. 2 to the third power is 8 minus 1, 7. So these are all my coordinates here. Now, I'm going to do of the derivative here. Of the derivative, the whole derivative. At -2, so f prime of -2 is going to give me 4 times 3, 12. I have a positive slope of 12 when x is -2. At -1, that's going to give me 1 times 3, 3. 0, 0, 1, 3, 2 is 12. So what this means is at -2, let's see, what color didn't I use? Let's try that one. Okay. At -2 of my original function, my slope here is positive 12. At 1 of my original function, I'm sorry, -1, my slope is 3. At 0, my slope is 0. At 1, my slope is 3. At 2, my slope is 12. Yes, no, maybe? On occasion? Did my amazing drawing of Mario help this problem?
You look like a bunch of mumble jumble.
You look like a bunch of mumble jumble. Alright, so this is the same thing that I did. It is a graph of the derivative and a graph of the function. At every single point, you could actually draw a line and have your tangent on that one right there. Okay, for all those. And so the derivative says right here, my slope is 12. So at -2, my slope is positive 12. -1, my slope is 3. At 0, my slope is 0. At 2, my slope is 12. And when it comes time to graph these things, there is graph paper there and rulers to make sure you guys got this. I am going to leave off today. I'm not going to do this one. I want you guys to start working on this. And make sure you all like, share, and subscribe. Hit that notification button, support my channel. Buy stuff from the merch store. The hoodies are on sale.